we're going to look at infinite series and infinite sequences. This is just an introductory video. It's not going to cover the entire thing, but just give you a short taste of what we'll see as we study these things in the future. We're going to start off talking about what are known as rational numbers. Rational numbers are numbers that can be written as an integer divided by an integer. Remember, the integers are 0, plus or minus 1, plus or minus 2, and so forth. So 6/11 is a rational number. Negative 11/6 is a rational number. Negative 156 is a rational number because it can be written as an integer divided by an integer. 355 over 113, my favorite rational number, is a rational number because 355 over 113 is an integer divided by an integer. Irrational numbers, what are they? Things like pi are irrational, and radical 3, natural log of 2, e, those are all examples of irrational numbers. Even something strange like radical 2 to the radical 2, that is an example of an irrational number. You may have learned that rational numbers, when you look at their decimal representations, they either terminate or they repeat. 6/11 is a repeating decimal. 355 over 113 is also a repeating decimal that has 112 digits that repeat before we start to see it again. On the other hand, irrational numbers, if you look at their decimal representations, they don't stop and they don't repeat. Pi, for example, looks kind of like 355 over 113, but after you look at 112 digits, the next 112 digits don't resemble the first 112 digits at all. And in fact, no matter how many digits we look at, you'll never have that repeating pattern. Going to look at an interesting number now. This is known as Champernoun's constant. We want to know maybe, is it rational or irrational? Well, let's understand what this constant is. You start off at the decimal place, and then you start counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and so on. That's that particular constant. Is it rational or irrational? If we think about the decimal representation business, if it stopped, then it would be rational. Well, we know this thing is going to go on forever. Could it repeat? If it repeats, it's rational. Well, a little bit of thought will convince you that it can't repeat. No matter what chunk of digits you think it might repeat, eventually later there's going to be another chunk of digits later that's going to be something different. So this guy turns out to be irrational. Think about how your maybe 6th or 5th or 7th grade teacher would ask you to speak this number. For example, when you learned 0.7, your teacher probably said, hey, don't call that 0.7, call it 7/10. Well, you could do that because it was a finite number of digits. This one you can't do that with. But we could do that digit by digit. We could say it's 1/10 plus 2/100 plus 3/1000, and so on. So it would look like this. You could look at them individually. There's 1/10, there's 2 100ths, 0.02, 0.03 we'd say 3,000ths, and then lots of zeros and a 9, we'd say 9 somethings. Well, the next one is not going to be 10 over 10 to the 10th. You might think it is, but because 10 occupies 2 digits, it's actually 10 over 10 to the 11th. And the next one is not going to be 11 over 10 to the 12th because it occupies 2 digits. It's 11 over 10 to the 13th. So there's not really a nice way we could say that, like we said 0.7 is 7/10, but you could say individual digits. I don't like that pattern breaking. You know, the exponents of the power 10 went 1, 2, 3, 4 up to 9, and then they skipped 10 to go to 11, and then skip 11 to go to 13. I don't like that. Let's make up a new number. And let's not look at the decimal representation yet. Let's look at the sum of these things. Let's make it so that those powers go up by 1. So 9 over 10 to the 9th is followed by 10 over 10 to the 10th, which is followed by 11 over 11 to the 11th, and so on. We're going to introduce a term that we'll learn very early in our study of sequences and series. What is a sequence? A sequence is just an ordered list of numbers. What do we mean by that? Well, it's just, like I said, it's a list of numbers, but they come in a particular order. That's the layman's approach to what a sequence is. A mathematician would say that a sequence is a function from the natural numbers to the real numbers. Yes, that's true, but we'll just look at the ordered list of numbers terminology instead. We can form lots of sequences from this particular sum. One sequence we could do is just to list the things that we're adding up. 1 1/100 or 1/10, and then 1/100th, comma, not 1/100th, 2/100ths, comma, 3,000ths, comma, 4/10,000ths, comma, and so on. That's a list of numbers, and it's in a particular order. We could take just some of the terms, like let's take the odd ones, 1/10 or 3,000ths, and then next 5/100,000ths, and so on. Or we could take a sequence that consists of the terms where the numerator is a perfect square. Interesting sequences. If you look at the long-term behavior of each of these sequences, you'll notice that the denominator is like growing in the number of zeros that it has before we can write it down. Like n over 10 to the nth. That's going to have lots of zeros before we can write any number down. And what I'm trying to say here is that n over 10 to the nth is going to be really, really small when n is big. That means it's approaching 0. So each of these sequences approaches 0, and we'll say they converge to 0. You may have remembered terminology from improper integrals, where we talked about integrals converging or diverging. We're saying that these sequences converge to 0. How do we add them up, though? Because we want to know what this sum is. Well, summation, when we add things, the addition symbol is what we call a binary operation. It takes two numbers, that's the bi part of binary, it takes two numbers and spits out one number. So that's a binary operation. You can't just add up an infinite number of terms. Here's what we do instead. We'll look at what's called the sequence of partial sums and see what happens to that. So from the sequence of terms, we're creating a new sequence, which we call the sequence of partial sums. Let's just take the first term. What's it equal to? 0.1. Let's add the first two terms, 1/10 plus 2/100ths, 0.12. The sum of the first three terms, 0.123, or 123 thousandths. If we look at the sum of the first four terms, we get 617 over 5,000. So this is what we call the sequence of partial sums, and we'll give them a new symbol. S sub 1 is the first partial sum, S sub 2 is the second partial sum, S3 is the third, and so on. Well, if we keep this up, the ninth partial sum would be the sum of the first 9 terms, which is 0.1, 2, 3, 4, 5, 6, 7, 8, 9. Let's look at the 10th partial sum by adding 10 over 10 to the 10th to both sides. The problem is that the 1 in the tens place of the 10 that we're tacking on at the end bumps into the 9 that was kind of there at the end of that number, and we're going to have to do some carrying. So 9 plus 1 is 10. We would put a 0 down in that very last column, and then we would carry the 1 to where the 8 is. So this turns out to be 0.1, 2, 3, 4, 5, 6, 7, 9, 0. It's as if we somehow forgot the number 8. That means the ninth partial sum, as we said, was 1, 2, 3, 4, 5, 6, 7, 8, 9. The 10th partial sum is 0.1, 2, 3, 4, 5, 6, 7, 9, 0, 0, 0. The 11th partial sum, we would tack on an 11 at the end, kind of-ish. And the 12th partial sum, the 1 in the 12 that occupies the tens place would bump into the 1 in the 11 that occupies the ones place there. Let's not look at that actual sum. Let's look at something else and do a sequence of partial sums. It's very much related to that. Powers of 10. Well, 10's a big number. I don't like 10. How about 2? What if I replace all those powers of 10 by powers of 2? Let's look at the sequence of partial sums we would get from that. The first term is 1/2. That's 0.5. The second term is 2/4, which reduces to 1/2, so the second partial sum is 1/2 plus 1/2, which equals 1. The third partial sum turns out to be 1.375. Now, I could bore you by doing more calculations, but what I want to know is what happens to the sequence of partial sums long term. So we're going to look at a large number of terms, not too large. The sum of the first 20 terms turns out to be 1,048,565 divided by 524,288, which as a decimal is 1.999979 blah 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 blah. The first 4 digits after the decimal point are all 9s. You might get a sense that this thing is getting close to 2. If we go to the 21st partial sum, it's probably a little bit more than that, but not going to exceed 2. We're going to see if we can figure out whether or not this is true. Does that particular sequence or series converge to 2? Well, we started off with the ones with 10s in the denominator. powers of 10. We changed it to ones where we had powers of 2 in the denominator. What if we changed it to a different set of powers? How about negative 0.67? I just made that number up. There's no significance to it. I don't know. What we could do here is we varied something, right? We varied the power that we were raising. We're going to see, you might be easier to see this a little bit later, but rather than saying this is 3 over something to the third power and 4 over something to the fourth power, let's think of that 3 over 10 cubed as 3 times 1/10 cubed. And the 3 over 2 cubed is 3 times 1/2 cubed. And the 3 over negative 0.67 cubed as 3 times 1 over negative 0.67. The things that we're raising to power have varied, and so we could represent it sort of generically by this function. I'm calling it f of x, and I might be really treading on some shaky math ground here. Turns out we're pretty secure, but we probably should be careful with what we're doing. But each of these series that we have, a series is an infinite sum, each of these series looks something like x, some number x, plus 2 times that number squared, plus 3 times that number cubed, and so on. We can write it in handy-dandy summation notation using the sigma, the Greek letter sigma. Each term is of the form a number times x to that number, n times x to the n. Or the first term starts when n is equal to 1, and we go on off to infinity. We want to know the values of f of 1/10. That would be the first sum that we wanted. F of 1/2. We think f of 1/2 is equal to 2. We're not sure. We're going to see if that's true or not. The last one we would do would be f of negative 1 over 6.7. Let's see if we can figure out what these are going to be. Like I said, we don't know what f of 1/2 is, but we think it is equal to 2. Look at those terms. Aren't they beautiful? It looks like every single term has an x in it. An algebra student, when they see something where everything has an x in it, is tempted to factor it out, which I think is a good thing to do. Let's factor that out. Now, think as a calculus student. Actually, think as a calculus 1 student. A calculus 1 student should look at each of those terms and say, hey, those look familiar. 4x cubed. 4x cubed was an answer to a question, in the same way as 6x to the 5th was an answer to some other question. Isn't 4x cubed the derivative of x to the 4th, and 6x to the 5th is the derivative of x to the 6th? So each of the terms inside the parentheses looks like the derivative of x to some power. And so that's what I'm going to do. I'm going to replace the stuff inside parentheses with a derivative of a function that would give us that. And I'm going to cheat here a little bit too. It's x times the derivative of 1 plus x squared, and so on. The derivative of x to the 6th, the very last term that I see there, is 6x to the 5th. Now I cheated a little bit. I snuck somebody in there. The first term inside the parentheses is 1, but the derivative of 1 is 0, so I can put that in for free. I did 1 to be consistent because that's x to the 0th power. X to the 0th power is equal to 1. If you look from the third line back to the second, you'll agree that that's equality. Well, what's the stuff inside the parentheses equal to? I don't know, so let's give it a name. Let's call it S. And we are now treading on very shaky mathematical ground, so don't quote me on all this. It's true, but there are some conditions under which it's true, and we're not going to discuss those conditions. But let's let S be the sum of those things we're trying to add up. Well, every single term has an x in it. We're going to do something sneaky. We're going to multiply both sides of this equation by the letter x, or by the variable x. When we do that, I'll get x times s on the left side. The first term would be 1 times x, which is x. The second term would be x times x, which is x squared. X times x squared becomes x cubed. And so we end up with the sum that's on the bottom. Now I shifted all of those products, x times 1 plus x times x plus x times x squared, I shifted them one place to the right so that they lined up perfectly with the powers of x above it. On the right side, the top equation and the bottom equation are identical with the exception of the 1 at the beginning on the top equation. So if we subtract the bottom one from the top, we'll lose all those x's. Let's subtract the bottom from the top and the left side. That would be s minus xs. If we subtract the top minus the bottom on the right side, as I said, all those powers of x will go away, you get 1. Now an algebra student, once again, wants to know what s is equal to. On the left side we have s in both terms. You can factor that out. And then we have s times something equals 1, and so we're going to divide both sides by 1 minus x, and that sum is equal to 1 over 1 minus x, only for certain values of x, which we'll deal with as we cover this material later on in the semester. So I'm going to leave that down there in the bottom right corner because I need that. The sum was the stuff inside the parentheses. So instead of x times the derivative of the sum, I can say it's x times the derivative of 1 over 1 minus x. We need to put 1 over 1 minus x in a derivative-ready form. So let's bring the 1 minus x up from the denominator. So it's 1 minus x to the negative first power. When we take that derivative, we'll bring the negative 1 down. We subtract 1 from the exponent to give a new exponent of negative 2, and we multiply by the derivative of the inside. So the negative 1 right before the equal sign is due to the derivative of the inside. If you look at everything on the left there, on the very bottom line, you have 2 factors of negative 1, which will multiply to give you positive 1. 1 minus x to the negative 2, we could stick that in the denominator as 1 minus x squared. So let's summarize what we've got here. We started off creating this function, which was x plus 2x squared plus 3x cubed, and we just concluded that we think it's equal to x over 1 minus x squared, and it is equal to that only for certain values of x. We are not going to talk about which. We'll keep that a secret. We thought f of 1/2 was equal to 2. If you put 1/2 into this equation, you get 1/2 in the numerator. In the denominator, we take 1 minus 1/2, which is 1/2. If we square that, we get 1/4. 1/2 divided by 1/4 is indeed 2. What about our original one? We were looking at 1/10 plus 2/100 plus 3/1000. Well, if we substitute 1/10, then we get 1/10 over 1 minus 1/10 squared, which becomes 1/10 over 9/10 squared, and after we simplify, we get 10/81. And if you put that into the calculator, you will indeed get 0.123456790, and then that repeats 123456790, and so on. What about the crazy one? There's no point in doing this. It's just an exercise at this point. Negative 1 over 6.7. Well, I convert that to fractions because I like fractions better than decimals. And so it turns out to be negative 670 over 5929, whatever that is. There's no significance to that number. It was just to make a point. Some parting shots. What did we do? We looked at what a sequence is. A sequence is an ordered list of numbers. We know a sequence converges if the terms approach some value. Okay, and so formally, the sequence converges to a number L if the terms of the sequence can be made as close as desired to L by looking far enough out in the sequence. So if we think something converges to pi, that means that the terms get really close to pi, but you have to look far out in the sequence to get a certain desired level of accuracy. What is a series? A series was just a sum of the terms of a sequence, and we knew a series converged when the sequence of partial sums converged. That's an important concept to get in mind. Some things that we'll see. This was not covered in the video, but we're going to talk about different tests to determine if a sequence converges or if a series converges or diverges. We have the divergence test, an integral test, which I bet you're going to see some integrals with the integral test, a limit comparison test and the comparison test, alternating series, ratio, root tests. Those are things you may see as you study these things. What else can we do? Well, we could look at sums of reciprocals of numbers. How about sums of reciprocals of primes? Does that converge? I don't know. How about sums of reciprocals of integers where if the number has a 9 in it, we toss it out. So 1/9 is not allowed to be part of our sum, nor is 1/19 or 1/29. 1 over 90 isn't allowed to be a part of our sum. What happens to that? Does it converge? If it converges, what does it converge to? What does that value equal? Okay. We're going to go from things that involve just particular terms into things that involve variables, like we did in our example. Can we take something on the left side and write it in a simpler form, like we saw the sum of powers of x was equal to 1 over 1 minus x? Well, I already told you, sometimes it's not always exactly equal. Maybe it's only equal to a simpler form when x is maybe between negative 10 and 10 or something like that. And if somebody tries to tell you that 1 plus 2 plus 3 plus 4 plus 5 plus 6 or something like that is equal to something, in particular if they try to tell you it's equal to negative 1/12, do not believe them.